In this video, we will state some key theorems about continuous functions. So the first theorem says the following types of functions are continuous at every number in their domains. All right, so polynomials. So let me give an example. So something like f of x equals negative 3x to the fifth plus 7x plus 12. Rational functions as well. So rational functions are polynomials divided by polynomials. So for example, something like negative 3x over x squared minus 1. That'll be continuous at every number in its domain. So real quick for this one is going to be continuous everywhere. Everywhere except the numbers that are not in the domain, which are the things that make this denominator 0. And those are x equals plus or minus 1. Root functions are also continuous everywhere in their domain. So a root function is something like the fourth root of x. So a root function. Trig functions like f of x equals tangent of 2x. Inverse trig functions. F of x equals sine inverse of x. That would be an inverse trig function that's continuous everywhere in its domain. Exponential functions. An example is f of x equals 2 to the x plus 1. An exponential function is a function that has the variable in the exponent. And logarithmic functions. So things like f of x equals ln of x. Okay, so all of these types of functions are going to be continuous at every number in their domain. The next theorem talks about combining continuous functions. If f of x and g of x are both continuous at x equals a, and c is a constant, the following functions are also going to be continuous. Okay, so the first is if you were to take f of x and either add or subtract g of x to it, that will also be continuous at x equals a. If you do a constant times one of these functions, that will be continuous. Also, if you multiply two continuous functions, f of x times g of x, that'll still be continuous at x equals a. And if you divide, if you do f of x over g of x, that's going to be continuous at x equals a as long as g of a is not 0. So as an example of how we could apply this, sine x is a trig function, and that was one of the things in this list that's continuous everywhere in its domain. And then e to the x plus 1 is an exponential, so that's going to be continuous everywhere in its domain. If you multiply these two, this is going to be continuous everywhere. Everywhere. Since sine x and e to the x plus 1, those two pieces are. And this previous theorem says when you multiply two continuous functions, that product will also be continuous. All right, so there's one final theorem that I want to state. And this says, if the limit as x approaches a of g of x equals some number b, and f of x is continuous at b, then the limit as x approaches a of f of g of x. So if g of x is inside of f of x, we can move that limit inside of f, inside of that continuous function. And we'll get f of the limit inside x approaches a of g of x. So in words, this is saying that we can pass a limit inside a continuous, I'll just abbreviate, continuous function. So as an example, if I needed to do the limit as x approaches infinity of ln of some complicated stuff, I can move that limit inside of the ln to get this will be ln of the limit as x approaches infinity of that stuff. Assuming that the limit of this stuff is a positive number, so that ln will be continuous there. So this theorem, we'll see this more in section 4.4 when we talk about something called L'Hopital's rule. In terms of our goals for this section, we finished goal 3, which was to list some key theorems about continuous functions.